live now. Welcome, everybody, to our PTt-talk 8 with Professor Silvio Ferrero. We are here today with Professor Brenda Rocha from São Paulo, University of São Paulo, and with Carlos Ganadi, researcher of the Brazilian Geological Survey. Thank you, Silvio, for coming to give us today this nice talk about nanogranitoids, nanorocks, and other tiny droplets.
Thank you for inviting me.
Welcome everybody, and thank you, Silvio, for attending this invitation. So we are here again with another talk on petrochronics, which is an initiative that includes Brazilian researchers and collaborators, international collaborators, with the focus on dissemination and investigation of petrochronological techniques, and mostly for understanding the geodynamic evolution of our planet. So most of our actions is organization of events, talks, workshops, and meetings, always open to the community. So we are also present in the social medias such as the YouTube and Twitter and Instagram. So if you want to know more, just go there and make your research.
Okay, good morning, everyone. Thank you, Silvio, for being our speaker today. So I'm going to give a brief introduction about Dr. Silvio Ferrero. He's a newly appointed associate professor at the University of Cagliari in Italy, and a guest visiting researcher at the Leibniz Institute in Germany, and also in the museum in Berlin. He obtained his bachelor and master degree at the University of Torino in Italy, and he obtained his PhD degree at the Geoscience Department in the University of Padova in Italy. So he has been conducted postdoctoral research funded by Alexander von Humboldt at the University of Potsdam in Germany. He has been working on metamorphic petrology with the investigation of nanogranitoids and nanorocks. So thanks again, Silvio. It's a pleasure to have you here, and we are looking forward to your talk.
Okay, thank you again for inviting me, and good morning, everybody from the other side of the pond, and good afternoon, everybody from this side in Europe. I hope you will enjoy this talk. It's about the research I've been doing for the last 10 years, I would dare to say. And so, here we go, nanogranitoids, nanorocks, and other tiny droplets. So, in this talk, I'm going to show you why it's important to work on micropetrology of inclusions, and why the study of nanogranitoids has a strong impact on our understanding on anastasis. Then I will tell you about why we started all this, what we were expecting, what we got, and also about the last point, what we didn't expect, but we still got. So some new discoveries. So micropetrology of inclusions. As metamorphic petrologists, when we take a metamorphic rocks such as this beautiful perpotassic granulite from Blanskieles Massif in the Moldanubian zone, we are interested in understanding what has been going on with it. We want to define the PTt history of these rocks, and in order to do so, we go and look at the main assemblage of these rocks. In this case, a very simple assemblage, biotite, feldspar, garnet. By looking at the main components and using some previous knowledge, some modeling, whatever you may like, we can get some information about, hopefully, the metamorphic peak, but mostly about the reequilibration processes that have interested these rocks, because unfortunately, most metamorphic rocks are heavily reequilibrated. However, when we go to look inside a good mineral such as garnet, we can find a second level of information, which is represented by inclusions. If we are lucky, these inclusions can tell us something about the metamorphic peak conditions, and in some cases, the prograde history that this rock has undergone. For instance, the reactions that formed the metamorphic peak assemblage. So we can easily say that inclusions represent small windows in the rock's history, and these windows are extremely consequential, and this is a very good example, in my opinion. The finding of coesite and diamonds in metamorphic rocks showed that crust can be subducted very deep in the mantle, depth in excess of 140 kilometers. Of course, this idea is now partially challenged by the new findings of elastic geobarometry, but in some places for sure is still true, so let's keep it that way in this moment. The other consequential type of inclusions, which is the one I'm working on, are melt inclusions. So it's almost 300 years that people take microscopes and put some slices of rocks under them to investigate their properties, or just to try sometimes. And since the beginning, they started finding tiny droplets inside these minerals, and already in 1858, H.C. Sorby from the University of Sheffield in UK was the first to publish the very first paper on melt inclusions, mostly in magmatic rocks, as well as in slugs left over from smelting of ore materials. And as you can see, they are pretty nice drawings, if I may say. And these inclusions have been investigated for 150 years now to understand better magmatic processes. Now, 150 years later, in 2009, thanks to the intuition of Bernardo Cesare from the University of Padova, we are looking at melt inclusions in metamorphic minerals. These can be used as tools to investigate the production of melt at depth, in other words, to study crustal reworking, and in particular, anatexis, by looking for crystallized melt inclusions or nanogranitoids. Which is the connection between anatexis or remelting and nanogranitoids? Well, when we look at the crust, in most cases, the crust undergoes melting via a reaction that involves a certain amount of phases, plus minus fluid, and then ends up producing granitic magma plus perictetic phases, mostly garnet, and again, maybe some fluid. Because the granitic magma that comes out from these rocks has not the same composition of the original rock, and because there is a solid portion being produced at the same time, we call this partial melting. So these melts that are generated are, as I said, granitic, and they are more buoyant with respect to the surrounding solid rock, so they tend to migrate to shallower levels of the crust. This means that they bring silica, potassium, sodium in the upper crust and leave the lower crust enriched in other components such as iron, magnesium, aluminum, and calcium. What does it mean? It means that anatexis is the main engine for chemical differentiation of the crust. It causes the remobilization and the reconcentration of elements of economic interest. It releases H2O and CO2 from the lower crust into the upper part and into the atmosphere, and changes crustal rheology. Of course, a partially melted crust is weaker than a subsolidus crust. So we are very interested in quantifying anatexis. However, the biggest roadblock that we find immediately is which is the composition of the original melt. So we know that melting in the lower crust generates large granitoid bodies in the upper crust, especially S-type granites are famously generated via crustal melting, at least in part. However, it's not a good idea to study granitoids in order to understand the composition of the original melt, at least not alone, because as you can see in the figure on the right from Carvalho et al. In 2017, between the partial melting down there at the bottom of the diagram and the end product, the granite, there is a lot of stuff happening. So each one of these processes will change the composition. This means that the granitoid body is not representative anymore of the original melt. However, we know that if we go deep in the crust, we find migmatites. What are migmatites? Migmatites are mixed rocks which contain indeed an unmelted portion, generally named melanosome, and a melted portion, now crystallized, of course, that used to be melt, called leucosome, with mainly quartz, plagioclase, and gate feldspar. These beautiful rocks are from the Kerala-Kondalite belt in southern India. And yes, this is melt, but even in this case, we are not sure that this melt has been produced indeed exactly there from that sample that we have in the picture. It could be infiltrated from somewhere, it could have lost components. Again, it's not good to study leucosome to get the original melt. But luckily, we have garnet. I mean, garnet is the most beloved mineral by the petrological community. I'm sure it is, at least for metamorphic petrologists. And luckily for us, garnet is the peritectic phase of preference for partial melting processes in the crust. In fact, here you can see a few garnet. If you are lucky, you collect a piece of rock, you make a nice thin section, well polished, and you can see that the garnet occasionally contains these little dots, okay? Initially, these may look like defects in the sample preparation, but when you go and look at them in details, they turned out to be tiny aggregate of phases that in the complex constitute a granite, and for this we call them nanogranitoids. Now, one can argue is that the very first melt that appeared in the rock is coming a little bit later. In my opinion, this is, everything we can say is this as close as we can get to the natural melt. This is the best we can do at the moment. We cannot be there while they are melting, and I'm pretty sure that we are pretty close with this kind of melt inclusions. Now, you would say, oh, my melt inclusions, they are definitely a magmatic affair. No, this is not true, as it has been recently proven. They are also metamorphic rocks. At the end of the day, the basic principle of fluid and melt inclusion studies is that every mineral growing in presence of a fluid, and there are many, and you can also say, instead of a fluid, a melt, these minerals may trap some portions of this fluid. And a normal melting reaction, such as the dehydration melting of biotite, is a perfect example of that. You have biotite, plagioclase, ilmenite, and quartz reacting, giving magma or melt, garnet, in some cases feldspar, some cases fluid, but you have garnet growing in presence of melt from the very same reaction. So while in magmatic rocks, the melt inclusions are trapped while the host, it could be a olivine, could be a quartz, are crystallizing on cooling, thus trapping their parental magma. In the case of nanogranitoids in garnet, this process happens on heating. So what we have is the garnet being cogenetic with the melt and trapping this melt that is basically its brother being created by the same reaction. So I wanted to give you an idea of how they look like so you can try to look for them yourself in your samples. Well, the first thing is that they are small, absolutely small. People rarely get it, how small they are, until someone shows them a proper sample under the microscope sitting together in a lab. This is not possible nowadays, unfortunately, but I'll do my best. So as I say, they are small. Take a look of these scales on these pictures. We are talking about up to 25 microns when we are lucky. There are exceptional cases above 40 micron, but yeah, they are small. In most cases, they are polycrystalline aggregate of phases. And how do you verify that? Just with a simple optical microscope, you go and look at high magnification cross polars if there are multiple birefringent phases. If you have multiple birefringent phases, then you have a good chance that this is indeed a nanogranitoid. Generally, they are often isometric. A part of these inclusions that we find in clusters in the garnet are composed of purely glass, or like in this case, in the lower part of the screen on the right, you have glass plus rutile. So this glass, of course, will be isotropic under cross polars, but of course you have to go and verify if this is really glass, because it could be, well, pretty much anything if it is black. So we do some field emission SEM observations, and what we see is that these nanogranitoids contain, again, an aggregate that is consistent with the crystallization of a silicate melt. Let's talk about silicate melts for now. And as you can see, they can be identified via EDS mapping. If they are big enough, you can do some microprobe analysis, or, for instance, Raman spectroscopy. In this case, you have several cases of inclusions that show a very regular shape. This is the so-called negative crystal shape, which is inherited or imposed actually by the host garnet on the melt itself before crystallization generally. And these inclusions can be also partially crystallized, like the one in the bottom left figure. And then they can be also completely glassy, as I showed you before. And this is a beautiful piece of glass. This is actually a giant as glass inclusions come. They are generally very small. Now, we started all this business because we wanted to know the composition of the melt. But yeah, I show you these nice pictures and these nice structures, and you tell me how the hell can we measure something that small? Yeah, one could think about doing measurements on the single phases and then do a mass balance, but there are many errors that can be inserted in this procedure just because of your personal bias toward darker colors, lighter colors, and so forth. And in any case, it will take time, even if you use some automatic kind of software for this kind of survey. So the only inclusions that we can analyze directly are the glass inclusions because they are homogeneous. And the problem with these guys is that, well, they are, in general, they represent less than 10% of each cluster of inclusions that we find in natural rocks. So this means that you don't collect many data, and very often they are small. I mean, the one, as I said, the one here in the picture is a giant. Generally, they go down to 5 microns across, even less. And under those conditions, it becomes really tricky to analyze them with any kind of microprobe, even with a field emission probe, because you start losing alkalis, you need to correct for that, and you're never sure if you can do it correctly if they are too small. So how do we solve this problem? Well, we make them glassy again, so we make them homogeneous. But how we do that? We need to proceed via experimental remelting. Now we have to think about where and when these processes are taking place. I mean, if we look into this diagram, the wet granite melting is, well, very high temperature as expected, but most importantly, it spans across a wide range of pressures, really from close to the surface to down to the stability field of diamond. And what does it mean for our experimental remelting desire is that it means that if we try to reheat this inclusion just by using a common heating stage, such as the one that are used for melting inclusions in magmatic rocks, what you cause in these inclusions is a straight up increase in pressure. For instance, following this isochord that is reported in this diagram on the left. And as you start remelting the aggregate that is now inside the nanogranitoids, the pressure inside will increase rapidly until it reaches the pressure at which this droplet was completely melted. But generally, this pressure will be much, much higher than the ambient pressure. And what does it mean for the host? That the host give up. The host, the garnet, even if it is a stubborn and strong mineral, cannot keep up with this kind of evapopressurization. What you get is what you observe in the upper image on the right. You see a beautiful starburst, let's say, structure with this inclusion clearly exploded across several lines. And if you go to the field emission and you try to image that, you will see that, yes, we remelted the inclusion, we got glass, but this glass has created a lot of other products. So this means that this glass has reacted with the host, creating oxides, creating sometimes pyroxene. So that glass is changed, is not preserved anymore. We don't want that because we want the preserved melt that was at depth. For this reason, we cannot do that, and we are going to apply pressure at the same time of temperature. In order to do so, we use a piston cylinder. This is an image of the piston cylinder I use extensively for the last 10 years here in Potsdam. And we load into this piston capsules. The capsules can be made of platinum or gold, depending on how hot you want to go. We load them with silica powder, which contains pieces of garnet that contain nanogranitoids. This garnet can be just separates from grinding the rocks, if you're lucky enough to have enough, or chips, like the way I prefer, like more on the right of this image. You see chips separated by hand from double polished thick sections. In the last image, the C image, you see instead a core that has been drilled with a micro drill through a garnet containing inclusions. So we put this in our capsule, we keep it up at high pressure and temperature for a certain amount of time. We get full rehomogenization of the nanogranitoids. The PT conditions for our experiments will be defined by previous studies that were done on these rocks. We have to get an idea of when the garnet formed, trapped in this melt. With those data, we go and make our experiments. Luckily for us, garnet is a nice recorder of the history of our rocks. After they are fully rehomogenized, then they are ready for measurements, these inclusions. So you can analyze them with Raman, microprobe laser ablation, and even nanosims. Now, The whole business of nanogranitoids in migmatites started in 2009. Now it's 2021, so 12 years later, we have around 43 localities, just considering nanogranitoids in garnets, across the whole world. As you can see, so far, no nanogranitoids in garnet from Brazil, sorry guys, but it's just a matter of time. They will be there, I'm sure. And as well as Australia. Same there, sorry. But yeah, I'm sure that we will find them. And many of these dots in this map represent actually multiple findings. Probably the most important is this map of the Bohemian Massif, where I worked for the last, 5 years now, 6 years. And it turns out that in the Bohemian Massif, at the present day, we have at least 16 localities where rocks partially melted and trapped melt, going from 4 kilobars, 0.5 GPa, or 5 GPa, 0.5 GPa, down to 4.5 GPa, so over a wide range. Okay. Now, of all these case studies I showed you before in this map, roughly 25% of them do not only contain nanogranitoids, but they also contain fluid inclusions in the same cluster. And I specify in the same cluster because this tells us that they are all together randomly distributed in the host garnet. This means that the garnet was growing in presence of fluid and melt, both, at the same time under conditions of primary fluid melt immiscibility. Here in the image, you can see on the left a beautiful garnet packed with inclusions, on the right a detail of the same garnet with nanogranitoids reported with the red arrow and with the white arrow some fluid inclusions. Now, the study of these inclusions tells us that natural melts are often formed in presence of a COH fluid. I mean, this is not such a big novelty if you think about that, because in order to stabilize any silicate melt under crustal condition, you need water. What is interesting is that it is almost never pure water, it is a COH fluid, so there is a strong carbonic component. How do we analyze these inclusions? Because, well, even if they are on the surface, right there with the nanogranitoids, actually they are full of fluid, so once you polish them and you open them, the fluid is lost, so you cannot analyze them directly. What we do, we use laser ablation to target inclusions similar to this, but under the surface. And with this laser, we can actually get some nice spectra where the peaks show the presence of different volatiles, for instance, in these particular case studies, CO2, N2, and CH4, along with, in this case, pyrophyllite. So by using micro-Raman spectroscopy, we can tell which kind of fluid is still there next to the nanogranitoids. Now, I showed you why we should study them and where we found them, and I hope I gave you an idea of how to recognize them. Now, the work started, the business started with a task in mind, getting the composition of the garnets, of the melt that is hidden inside the garnets, and identifying the presence of melt. And in fact, now I'm going to show you some of these results. So the presence of melt in the rocks is something that, in my opinion, is not stressed enough. When you find nanogranitoids, you can actually say directly, especially if it is directly glass, you don't even have to rehomogenize them, you can say straightforwardly that there was melt in this rock at some stage, in particular in the stage of the PTT history where the garnet was growing. Now, this may be straightforward when you're working in migmatites because melt is everywhere in a migmatite, right? All these leucosomes. But when you have other kind of rocks, that's not so straightforward. For instance, I like to show this picture. These are contact metaphylites from Vedret de Ries in the Eastern Alps from the supplementary material of Cesare et al. 2015. I mean, these rocks have seen a lot of, well, troubles, a lot of processes. And yeah, you don't see any evidence for melt, right? Until you go inside the garnet and you see that they actually contain nanogranitoids. So that garnet grew in presence of melt, and there is no doubt about that once you verify that these inclusions contain a granitic or granitoid phase assemblage. This is another nice example. These rocks may look like almost just like granite, except that they are packed with garnet, so we are sure that it's a metamorphic rocks. These are high-pressure felsic granolites from the Polish Sudetes in the Bohemian Massif. I mean, you see a lot of white, but you cannot see a real leucosome domain, such as in a real migmatite. But when you go inside the garnet, you can see that most of these garnets indeed contain nanogranitoids sitting there toward the core. Another evidence for the former presence of melt is the fact that sometimes the garnet, such as the one on the left, has very nice euhedral shapes, for instance. So the melt was there, small amounts overall. After studying these rocks, I can tell you that, but it was there nevertheless. Now we come to the important part, the true melt composition and depth. So by looking at the nanogranitoids, we can finally analyze the melt at the source region, okay? If we put together all the data that we got over the years, we observe that, yes, nanogranitoids are trapped and occur in rocks equilibrated at many different PT conditions. Although, if you look on the left, from our paper, Nicoli and Ferrero in 21 on Geoscience Frontier, you see that most of these cases are sort of clustered between 750 and 950 degrees and between 0.5 and 1.5 GPa. So this is fully the granulite facies field, so makes sense. However, there are a lot of stray dots above in terms of pressure from with respect to this grouping of cases. And this means the nanogranitoids are also present in higher pressure rocks up to the stability field of diamonds. The fact that we have less cases is also due to the fact that those kind of rocks are much more rare than, let's say, lower to mid crust rocks. So, and then once you consider instead the distribution in time, you see that these nanogranitoids occur in rocks which melted across, well, large part of the history of the Earth, starting from 2.8. These are Greenland samples, all the way down to basically now. I mean, more recently, in a paper in PNAS, Jan Schönig from Göttingen reported the presence of inclusions which look like nanogranitoids inside garnets from Papua New Guinea. I mean, this is stuff that likely formed in the last 3 million years. So it's quite intriguing, actually. They span the whole duration of the Earth, which makes sense if you think about that. However, they are clearly clustered toward the Phanerozoic, so at less than 550 million years. So they are a Phanerozoic affair. But again, why is that? It is also possible, or it's more than likely, that all the rocks are more rare, so it's more difficult to find preserved nanogranitoids. Of course, now that we are focusing more on all the rocks, we start finding them. So I suspect it's just a matter of time. In this diagram on the right, you also see that the findings are divided by different protoliths. So what about the relationship between nanogranitoids and protoliths? So far, we have a lot of data on the felsic crust, meaning both metaphylites and metagranitoids. Well, because they are pretty much the most important component of the crust. And we know that the melting of this material generates S-type granites in the upper part of the crust. And indeed, when you compare the composition of all these melts that we find at depth in the source region, we see that most of the metaphylites have compositions that are located in the paraluminous field, while other samples, which are partially melted, nanogranitoids in partially melted metagranitoids, in particular the blue and green dots, are located more in the lower part toward metaluminous, even peralkaline in some location. So overall, what we can say is that these tiny bubbles of anatectic melt that we find in natural rocks represent embryos of S-type granites as proposed by Bartoli et al. In 2016, or even before, actually, probably it was already in 2014. But my point on this is that as we stand today, around 82% of the case studies refers to felsic rocks, only 10% to mafic rocks. And this is as of January 2021, based on the list that we report in Nicoli and Ferrero 2021. And well, that's something that needs to be rectified because mafic rocks are clearly underrepresented. And mafic melting, there is a general agreement that mafic melting plays a significant role in the birth of the continental crust, in the TTG production, and overall in the Archean evolution. So we need to understand those kind of processes, and we can do that by targeting nanogranitoids. So around 4 years ago now, we decided that it was time to fill that gap, and so we started targeting mafic melting processes, and I decided to set up our project on the Adirondacks. I mean, the Adirondacks is a beautiful place. If you've ever been there, you know what I'm talking about. If you've not been there, please go there. They're absolutely beautiful. They are basically an outlier of the Granville orogeny. They are just across the border from Canada into US. And probably most of you, especially if you like garnet, you know the existence of this magic place that is Barton Mine near Gore Mountain, which contained the largest garnet on the planet. In a historical record, they reported 1 meter wide garnets, which is almost impossible to believe. These garnets formed during the Middle Proterozoic, and still now you cannot find any more than 1 meter ones, but they are pretty big, as you can see on this picture on the left. You can see here Bob Darling, our Adirondack expert that guided us in our field trip, showing us how big these guys are on this freshly cut wall. And Bob Darling was exactly the reason why I decided to target the Adirondacks, because in '97, he reported in a publication that went on Science, I guess, the presence of polycrystalline inclusions inside this giant garnet. These polycrystalline inclusions were odd, and he proposed that maybe that was crystallized melt, but then there was no other work done on those. So we decided to take those samples and do a thorough job using modern techniques on exactly on those inclusions, and using our new perspective of nanogranitoid focused people. And well, it was a remarkable feat, and we got some very nice results, because these large garnets contain a huge amount of inclusions, and as you can see, they are nanogranitoids, all right, very nicely crystallized. In one case, we even found glass, so there was no doubt that this used to be melt. We published these results in EPSL, and in that paper, you can find that the composition of this melt is a trondhjemite. And in fact, when you compare this to the experimental results from mafic melting experiments, well, you can see that these trondhjemites are located right on one end of the whole data cloud, for instance, in the diagram B, the one more on the right. And if you can see, yeah, they are the circles, the white circles with blue rim. And it makes sense that they are trondhjemite, because we know that trondhjemites can be created by mafic melting. The rock that we are investigating is a rock basically made of amphibole plagioclase garnet, almost nothing else, a little bit of pyroxene, but that's it. So when you melt something like this, you will get either trondhjemite, tonalites, or something like this. Now, we took these compositions and we plot them in this diagram on the right against the SODIC TTGs from the database of Moyenne 2011. And as you can see, if we plot the vectors of the composition of some of the most common minerals that we find in these rocks, which are also the most common mineral that you may find in TTGs, we see that by combining minerals and melt inclusions, the melt that we find in these garnets, we can recreate most of the composition that we find in the SODIC TTGs placed in the upper part of the crust. So similarly to, we do believe that similarly to what we say for nanogranitoids in metaphylates being embryos of S-type granites, what we have here are nanotrondhjemites that are embryos of TTG-like melts that are trapped at the source region. Of course, you want more data on this, there is the EPSL paper. But moving forward, the second part of the signal, the second most important signal that you can get from nanogranitoids is related to the volatiles that are present at depth, because this thing tells us something about the fluid regime at depth during melting. Of course, you have seen the nanogranitoids are small. If you want to analyze volatiles, you need highly precise machines, high-resolution machines, and for this reason, we started using the nanosims in Paris at the Natural History Museum there. And here in the lower part of the screen, you see an image from Bartol et al. 2014, which shows in that square, you can see the exact space inside the inclusion that is sampled during the nanosims analysis. We are able to analyze a 1 micron square, basically, of material and get good results about the volatiles inside these melts. So we can say something about both speciation and amounts of volatiles during crustal reworking. At the moment, from lower crust, for instance, from the Vrea-Verbano zone, in this work from Carvalho et al. In the upper part of the slide, down to UHP eclogites from Seidenbach. This is a figure from the paper under review now in Nat Geo from my postdoc Alessia Borghini. And as you can see, we are covering already a wide range of pressures, and this is the result of an extremely huge amount of work that has been done in the last 6-7 years. Here, I just put this list of papers to show you how much work has been done recently in this direction. There is still more to do, but we are already getting excellent results. What do we need this data for? I mean, if you think about, we can know how much water is in the melt. We can calculate the melt viscosity at depth. So we can say something about how the melt migrates through the crust and then reaches the upper level after coalescing. In the CO2 business, of course, knowing how much CO2 is inside these deep melts is extremely important to evaluate the continental crust contribution to the global carbon cycle, which is the topic of some paper under preparation and under review at the moment. So that's a very nice part of the job, of the work on nanogranitoids. And a bit more in detail, at the beginning of this year, I published this paper in collaboration with Jay Agnew from Yale on some felsic granulites from the central main terrain. I mean, these garnets contain, again, nanogranitoids. We managed to rehomogenize them at more than 1,000 degrees, almost 2 GPa. The melt is granitic and paraluminous, as you expect from felsic granulite, with a possible metapelitic protolith. But the surprise here was given by the nanosims measurements, because we found that these melt contain sizable amounts of CO2, of fluorine. I mean, we have, in some cases, up to 9,000 ppm of fluorine. And then we also measure the chlorine with the microprobe. Again, almost in some inclusions, this is pushing toward 1%. So these can be interpreted based on previous knowledge from experiments and other observations as a proxy for the presence of brines at depth. What are brines? They are strongly saline fluids, which raised to prominence in the last years because several working groups has been proposing that brines can actually enhance or change anyway the productivity of melt in the lower crust by being present during melting. Most of these considerations are based on experimental work. As far as I know, what we present in this paper in American Mineralogist are the first direct measurements of preserved melt deep down, measurements of fluorine in preserved melt. So what we propose in these particular case studies is that brines were either present during the prograde evolution of these rocks, with the halogens being stored at some point in the biotite. Storing halogens in the biotite extend the stability field of the biotite, allows the biotite to give up only at very high temperature, around 1,000 degrees, much in excess with respect to the 820, 850 that are commonly proposed, and for the hydration melting of biotite. Or the other scenario is that brines were present deep down at 2 GPa while the melting was taking place. So we can discuss about that, of course. So as I told you, so far I wanted to show you what we expected, what we got. We expected data on the composition of the melt. We got excellent data on the composition of the melt and, of course, on the presence of the melt. But this field is still relatively new. It started 10 years ago, I would say. And you are bound to find new things when you're looking where nobody has looked before. And in fact, this is exactly what we did. In particular, one very surprising finding was that of crustal carbonatites. I started studying this beautiful garnet. I did a lot of work on this particular garnet from low-pressure metasediments which experience partial melting in the Oberpfalz in southwest Bohemian Massif. As you see, these garnets are packed with material, with inclusions, with mineral inclusions, and so forth. When we use cathodoluminescence, we actually see a very interesting feature. There are a lot of orange dots in this image that I show you on the right. What is that? Each orange dot is a carbonate crystal. Now, that was quite surprising. Why do we have so many carbonate crystals inside a garnet? So we did a very detailed field emission and Raman study, and we found that calcite, in particular, those carbonates are calcite, they are sitting in polycrystalline inclusions with a nice negative crystal shape, always along with chlorite and white mica. Sometimes there is also a little bit of quartz as an accessory. These inclusions sits in the same cluster with some nanogranites and some fluid inclusions, telling us that at some point in time when the garnet grew, there was for sure a silicate melt, something that then created these calcite-rich inclusions, and there was also fluid, a COH fluid, actually. So we wanted to rehomogenize the nanogranitoids. We did our piston cylinder experiments. In the same experiments where we achieved the rehomogenization of the nanogranitoids, we observed vesiculations in these calcite-bearing inclusions. If there is vesiculation, it means that there was at some point during the experiment some melt, And this melt, of course, now it's completely recrystallized, unfortunately, because I then discovered that if you look at calcium-rich melts, it's basically impossible to quench them to glass. I'm talking about, of course, calciocarbonatitic melts. This was difficult to sell because, of course, these are crustal rocks. There is no mantle input in the area. There is no mantle-related magmatism. We rehomogenized these inclusions at 800 degrees and 5 kilobars, 24 hours of duration for the experiment. So it was very difficult to sell because people expect carbonatites to be a mantle-related business. But then when you compare the composition of nanogranitoids and nanocarbonatites, I mean, everything fits. The nanocarbonatites are much more enriched in light rare earths, as you can see the orange lines in the diagram down there. Once again, in the ternary diagram, barium, rubidium, strontium, you see that the nanocarbonatites are much more enriched in strontium, as expected, with respect to nanogranitoids, which instead are more enriched in rubidium. So they have all the features typical of a carbonatitic melt, especially the high enrichment in light rare earths and strontium. But how do we explain that? How do we explain the presence of a carbonatitic melt, calcium carbonatitic melt in metasediments? Well, we proposed that this was the result of the melting of a column of sediments, which included a strong impure carbonatic element. In particular, we think that what was melting were impure marble lenses, which were packed inside these now high-grade metasediments. All of that happened in a sillimanite field, because these rocks basically only contain sillimanite. So we are very much at crustal conditions. So talking about carbonatites, this created some problem to the terminology, right? Because we started from nanogranites. The very first publication talks about nanogranites because the melt that we find is a granite, so a purely granitic melt. As we extended the investigation, we found more and more cases. We analyzed different silicate melts because, of course, the protolith is the first control on the composition of the melt that is resulting from partial melting. So it stands to reason to have many different types of melts. And in fact, we started talking about nanogranitoids after Bartol et al. 2016. Then I presented the nanocarbonatites, and more recently, by reevaluating all their literature, it looks like there were other kind of crystallized melt, for instance, nanoenderbite, reported by Dokokune et al. In 2014, which contains quartz, phlogopite, biotite, and even omphacite, and even nanocharnokites are reported by Galli et al. 2012 in the Groove complex in the Alps, and which contain a lot of OPX. So, quite timely, Bartoli and Cesare last year came out with this, very clear paper with a very clear title, Nanorocks, a 10-year-old history, where they indeed propose the use of a new terminology for this kind of inclusions, and this is the definition: minute-sized inclusion derived from a crystallization of an atectic melt and containing diverse solid phases, plus minus H2O or CO2. Well, actually, instead of or, there should be N or. But anyway, you got me. We talk about nanorocks now because the variability is much higher. So far, I showed you cases in which the origin of the melt is more or less clearly related to the host in which they occur. So the host is represented, at least in part, the original protolith that produced that melt. So with that in mind, when I started investigating, this was 2015, I guess, I started taking a look at these beautiful garnet pyroxenites here on the left from the granulate Gebirge, the northern part of Bohemian Massif. We started finding inclusions inside these garnets, beautiful nanogranitoids, as you can see here on the right. And the garnets are absolutely packed with them. I mean, they are everywhere across the whole garnet. So we took these beautiful samples and we found the money for a PhD project. And so Alessia Borghini took this PhD project and she started investigating these rocks. And my idea, but I was really convinced that this is the first case of nanogranitoids in high-pressure mafic rocks, then we call them eclogites after some more investigation, which was generated by the melting of these very rocks. It turns out that I was wrong, and well, I'm glad I was, because it's even more interesting. What we have here is actually metasomatic melt, because when we did the laser ablation of these inclusions, which is of course a powerful means to understand what was consumed during the partial melting process, we discovered that this melt had a clear continental crust signature with enrichment in cesium, thorium, uranium, and lead. That's not mental, even if these eclogites were sitting inside bodies of peridotites very deep in the mantle. So, yeah, it didn't make too much sense in the beginning. Then we compared these compositions to melt inclusions in metapelites, where the melt was generated by a dehydration melting of white mica, and there are many similarities. So what we said is that this was a metasomatic melt which infiltrated the eclogites at depth, caused a complete recrystallization, but they were originally originated from outside this body, from the melting of some felsic crust at very high depth. And the interesting part tells us that we are up to, we have a good idea to explain this, is that we find the same type of signature across the whole Bohemian Massif. So inside all these bodies that are reported here in the diagram on the right, so we have pyroxenites from a borehole, some peridotites, K-rich granitoids, the so-called durbacites, for those of you that know the Bohemian Massif. And when you compare them to the melt inclusions in eclogite, they show exactly the same kind of crustal pollution, if you want. And interestingly, we find, actually, Alessia found exactly the same also in the famous eclogites of Seidenbach, and this is one of the topics of the paper that is currently under revision. So, first kind of metasomatic melt has nanogranitoids, but for sure it will not be the last. Now, this is probably the most surprising of all the new discoveries, at least for me. We were interested in the bulk, but I was also interested in what is crystallizing inside these very small pores. So I spent a long hours at the Raman, here in our lab here in Potsdam, and I discovered that in most of our nanogranitoids, what we thought based on EDS mapping that was quartz, K-feldspar, albite, it is actually something else. It is a polymorph of these phases. So instead of quartz, we have cristobalite and tridymite. Instead of albite, we have cundicolite, which is an orthorhombic phase. Instead of K-feldspar, we have kochadavite, which is hexagonal. And instead of anorthite, we have a whole list of weird stuff that is called, for instance, dimisteinbergite and sviatoslavite. These are all polymorphs interpreted as metastable polymorphs previously reported somewhere else. And so we were wondering, why do we have this kind of weird phases? Most of these phases were originally found in diamond-bearing rocks. So in the early 2000s, people were proposing that, for instance, cundicolite and kochadavite could be phases represented indicating mineral indicators of UHP conditions. However, we started finding these very same polymorphs in inclusions that were trapped at much lower pressure, down to 5 kilobars. So definitely pressure is not a thing there. Even temperature is not really that important. What we think is causing the formation of these phases is the peculiarity of having silicate melt in a very small micrometric pore. And this kind of melt, under those conditions, experience delayed crystallization. This has been verified in other situations of fluid in small pores. What we proposed, for instance, in Ferrero and Angel 2018 on Journal of Petrology, that these inclusions, because the silicate melt is inside these micrometric pores, the melt itself doesn't crystallize at the solidus, but remain still melt underneath there. So it experiences supersaturation, undercooling, and all this situation leads to rapid crystallization when crystallization starts. And so we call them kinetically controlled metastable phases. We call these polymorphs in this, well, rather weird way, because we don't know any better at the moment in terms of better defining the formation condition of these inclusions. We already knew that something funny was going on in these inclusions because we have glass inclusions. Most of the samples of glass inclusions I showed you before are in rocks that cool down over millions of years. So there is no reason why glass should be there unless there is really an influence on the behavior on the crystallization behavior of the melt, because this melt is inside a small pore. There is still a lot of work to do on this, of course. Not only we have found these peculiar polymorphs with weird names, we also found brand new phases which we are currently investigating. In particular, we used Raman, microprobe, and now the FibTM to get information on these phases. They look very new. There is a phase that we call 412 based on the main peak in Raman, visible here on the left. This phase has the composition of an unmixed ternary feldspar, which is, well, unexpected. And instead, the phase that we call 430, that here you can see the Raman spectrum on the right, it has the composition basically of a tonalytic melt, including water, but it is crystalline, so it's really weird. Both of them have a structure that is similar to that of ozumilite, which itself is not that common. But yeah, we are doing the work, and hopefully I will be allowed to give some names of these new minerals. That would be pretty cool, actually. So far, everything I showed you so far in this almost 1 hour talk, it has been taken from inclusions in garnet. But garnet is not the only reliable container for inclusions. There is also zircons out there, and we know that zircon is an excellent container for inclusions. It's already the second most common host for nanorocks as of now, and it is stable over long periods of time. In fact, the oldest material on Earth is indeed zircon. So there is work to do there, and Maira Tedeschi indeed had a very good start on this topic by investigating these zircons from UHT mafic granulites from the southern Brasilia orogen. She identified a lot of nanogranitoids and investigated them with the Raman, which is not an easy task. It's very complicated when you have inclusions in zircon, because zircon is a very strong signal. She found that all these nanogranitoids contain indeed polymorphs. We even rehomogenized them already. More stuff is coming. So I would say we are almost done, and I would just like to thank all my collaborators, because this kind of work requires a lot of time, an excellent workforce, and a lot of workforce. So I would like to thank the Professor Patrick O'Brien, Alessia Borghini, Ber Wunder for the piston cylinder, Gauthier Nicoli, Falby van Schilden, Rico Fuchs, and Iris Vanov. These last two were my master students in the last couple of years. And then we had our long-term visitors, Maira Tedeschi and Gisela, which belongs officially to our team at this point. And I would like to thank Laurent Remosa for the help for nanosims investigation, Oscar Laurent, previously in Zurich, now in Toulouse, for the laser ablation ICP-MS investigation, and Chris Yakinchuk from University of Waterloo for the part on thermodynamic modeling of mafic systems. And of course, I would like to acknowledge the contribution of the many visitors to our Raman lab over the years, like Bruno Carvalho, Fabio Ferri, Omar Gianola, and Pavel Shrupsky. So in conclusion, I hope I convinced you that we can get a lot of cool data and even new stuff from investigating nanogranitoids and nanorocks. Most important part is that the age of nanorock is here, and we have to work on it, so we have to really get down cracking on that. And I would like to leave you with this beautiful quote from H.C. Sorby: there is no necessary connection between the size of an object and the value of a fact. And though the objects I described are minute, the conclusions to be derived from the facts are great. Thank you very much.
Thank you so much, Silvio.
Okay, everybody.
Do you want to leave it like this? Okay. It was amazing talk. I'm a bit biased to say, because I am enthusiastic of the topic. So I think Silvio has some connection problems. Silvio?
Yeah, it seems so.
I think so. In between, I want to invite everybody who enjoyed the talk to send their comments and questions. I hope we can reestablish the connection soon to continue the discussion with Silvio. I will ask just a minute to talk to him. Okay, he's trying to re-enter, and I think it's quite interesting that he has shown that we still don't have nanogranitoids described in Brazil, but if we have a closer look, I'm sure we will find in several minerals, and not only in garnet and zircon.
Yeah, but they show you something from the Minas Gerais.
Yeah, in zircon. So I went
yeah.
end of 2019, to Potsdam, and we worked on these samples that we investigated in the Socorro Guaxupé NAP, and it was quite nice that. So we found they are very tiny, and we were not sure in the beginning. George is saying that he might have some samples. Let's go for it to have a look. And we investigated, and it was quite funny because we performed the experiments and we were not sure about how to conduct for the conditions. And we used estimates from Brenda for PT conditions. And it was nice because when I was... so Silvio is back. Silvio? Can you hear us? No. Silvio?
Myra?
Hi, you are
Hi.
back.
Sorry, I'm
Can you
really
hear us?
sorry. Yes. I forgot to plug in the battery. Amazing. It just let me finish the thing and then...
Oh, it's amazing.
Yeah, in fact.
So Silvio,
Sorry.
I was saying how nice it was, the talk. Okay. And how fantastic it was, the talk. And said I was biased to say that because I'm very enthusiastic of the talk. And I was telling them about our experiments that just in the last day of Rama, in the last hour, we find out that they equilibrated. So we call it last minute.
Yeah, definitely.
Yeah,
That
so
was a last
we have
minute
some
trick.
comments from... Yeah, so I have some comments from the audience. I will add them here in the screen.
Okay. You can hear me well?
Yes.
Okay, perfect.
Yes.
Yeah, sorry, this thing going down was ridiculous. Okay.
So Silvia Volante is thanking for the talk. She said she really enjoyed it and the results are amazing and looking forward to the upcoming results.
Thanks.
Can I make a question?
Yes, sure.
Yes, go for it.
So Silvio, thank you for your presentation, which was really good, really amazing.
Thanks.
It's another word, yeah.
Yes.
So I have a question for you. So mostly about if there is someone working and trying to find nanorocks or in peridotites, mostly derived from an arc setting, for example, for looking for variations in compositions regarding to the rocks that we expect from arcs, for example, an Andean setting. I know that's hard to find a setting where you have the preserved peridotite, but is there anyone working with that, like looking at these nanorocks on these peridotites and cross-checking the variations that we have in an arc, for example?
Well, I mean, I'm not too much of an expert on that setting. There is people here, for instance, at the University of in Prague, working on polycrystalline or multiphasic inclusions. Those inclusions are mostly, I mean, they look like having been some sort of supersilicic fluid. Rather than an atectic melt. And in fact, in the definition of nanorock, I think that Bartoli and Cesar are very careful to say it must be a deep melt crystallized, you know? And so we cannot call them nanorock until we verify that it's some sort of melt.
Okay.
And in those settings, well, why not? I think it would be possible if the peridotites are embedded in some sort of pieces of continental crust. At some point, you may find something. But yeah, so far, what has been found mostly are multi-phase inclusions that show a composition more consistent with supersilicic fluids rather than silicate melt. And in fact, we were actually surprised when, I mean, finding this metasomatic melt in these eclogites from Alessia. I mean, these are long levels sitting inside the body of a peridotite. There is no network of you know, feeding veins that can show that the melt reached down there and sort of created all this mess that we see. And when you look in the peridotites around, they don't have any sort of inclusion whatsoever. So, you know, I'm sure that if someone starts looking at them, what I found is that when people study pieces of mantle, for instance, well, there is a sort of a preference toward geochemistry. So you take the rock, you smash it, and you do the geochemistry. Not many people spend a lot of time looking at the microstructures.
Exactly.
You know? Yeah. So I think that this is something that is missing. Of course, I mean, not everybody can do everything because the time is what it is, and you know, you have to find the money to have a project targeted at that. But so I understand why there is no time to do everything. But I'm sure that if people would start looking carefully inside all these rocks, you will find a lot of interesting things, lots. Like if they are not nanorocks, they are some complex kind of fluids. Then now another Brazilian, that is Bruna Carvalho, showed that it's pretty common to find fluid inclusions completely re-equilibrated on the way back when they are in the garnet. So that's even another tricky business that needs to be, you know, inserted in the vision of all this kind of fluids. I mean, I totally support the finding, absolutely. But yeah, it adds another level of complication to everything.
Thank you, Silvio.
Welcome.
So Silvio, Gisela is saying that it was a fantastic talk, that the new work you have present looks very interesting, and she cannot wait to read those papers. We are also looking forward to see yours as well, Gisela.
She's like you, she's partial.
And
so.
Yeah.
Thanks, Gautier.
So Gautier has also congratulated you and Beatriz, Bia, Cauê, and we have a question from...
Any melt inclusion in?
Wait.
Luvisotto said something. He said something.
Yeah. He asked if you have ever found inclusions in rutile, because he is enthusiastic of rutile.
Actually, you know, I never looked. But after looking into, I mean, I kind of avoided accessories until you came to Potsdam, because I thought that it was such a complicated world, and you know, it was a bit too much for me. But then after you came, I started getting interested in other accessories, and yeah, I mean, after zircon, monazite is the next one. Rutile, if one can prove that it forms under those conditions, which I have no doubt about that. No, I never looked into that, but yeah, something to look forward, definitely. So, thanks for the suggestion.
There is also, yeah, there's a question about Lucas Schiavetti.
Schiavetti. Maybe it's Italian. The name is Italian.
Yeah. So great talk, Silvio. Thank you. In order to investigate PT conditions of nanogranitoids with thermodynamic modeling, what is the process? Are they interpreted based on the garnet formation conditions?
I mean, short answer, yes. Because the point is that these nanogranitoids were originally droplets of melt. So when they were trapped, so they were trapped during the formation of the garnet. So if you can bracket the formation of the garnet, then you get the PT conditions of formation of that melt, or at least a minimum temperature and pressure at which that melt was stable with garnet, let's say, to be rigorous. Then, for instance, Omar Bartol in Padova pushed it forward and he started modeling the composition of the nanogranitoids as an isolated system per se. And that one gave some interesting results, for instance. For instance, there was a case from Kaligandaki in Himalaya where the nanogranitoids contain chlorite. And if you see chlorite growing inside a thing like this, you think that it is altered, right? But these nanogranitoids were perfectly preserved, and he did the modeling, and in this paper in 2019, he demonstrated, for instance, that you can create a chlorite in a closed system inside an inclusion without having to rely on any cracking on influx of fluid. So thermodynamic modeling on nanogranitoids itself is done and can give some very nice results indeed.
We also have a question from Otávio. He's asking, when characterizing the chemistry of melt inclusions in a rock sample, how many melt inclusions do you consider for a representative result? And then he has a second question. Do you analyze lots of melt inclusions and then takes an average composition, or do you consider the melt inclusion compositions individually?
Okay, so first, for the first one, it was, oh, God, I already forgot. Can you repeat it again? Sorry.
So how many melt inclusions do you consider as a representative result?
Finding these inclusions is, after the experiment, is a terrible job, because you have to take the capsule, you have to mount it in a pod, polish, bring the inclusions to the surface, verify that they are homogeneous with the Raman. So if there is no other phase other than glass, then go to the microprobe, analyze them, and then repeat. And that stuff takes a lot of time. So basically, let's say that in my papers, I tend to give like 10 to 15 analyses per paper, and that takes me generally months to do those data. The lowest amount of data used is 4 in one paper, because it was the nanogranitoids coexisting with the carbonatides. And back when I was in Virginia Tech, Bob Bodnar told me that the minimum amount is 3, because with 3 compositions, you can always make a line somehow. And so, but yeah, let's say that as many as you can, but then at the end of the day, you have to stop at some point. And yeah, it just depends how difficult it is to bring them to the surface and analyze them. And the second one, yeah, generally we consider I like to consider the average composition, because I think it is much more representative. Also because when you have those large clusters sitting inside your garnet, I mean, you have a garnet, you have 100 inclusions sitting there. All these 100 inclusions should have more or less the same composition. So, because if the garnet is homogeneous, it means that it was just one pulse of melt production with no changes in the reactants. So this means that also the melt that is resulting from the exact same melting reaction should have always a constant composition. So I like to work on averages, because you do your analysis, but things can always go a bit wrong. There could be some hidden trapped phase that is going to mangle a little bit your number. So I like to do as many analyses as I can, and then averaging them. I think it's more realistic than going for each single inclusions.
Nice, thank you. It was a very interesting talk. I also have a question. So okay. I'm interested in the difference of approach that you've been using with the garnets I mean, in the Bohemian Massif that Alexia Borghini worked extensively, we know that the garnets are really tiny in these felsic high-pressure granulites when we compared to the Adirondack garnets that reach up to 1 meter size. Yeah, they are really, really beautiful. When we met in Boston in 2018, you just came back from the field and you showed me lots of pictures and yes, really, really nice. So on the your experiments to get the true composition of the melt, so you from the Bohemian Massif garnets, you were looking for the glassy inclusions, and you were taking the whole pieces of garnets inside the platinum gold capsules, right? When you're doing the experiments. So what's the difference of approach when you analyze these tiny inclusions from, from tiny garnets with the ones from the, 1 meter size garnets from Adirondacks? I mean, the sampling, how do you consider these inclusions to be representative in very large garnet porphyroblasts?
Well, at the end of the day, the important point is that the host. Okay, when you look at the nanogranitoids, you don't know their composition when you start with them, right?
Yes.
So the important point, but you're making the assumption that they are trapped while the garnet was growing. And as I said before, if there is no change in the reactants, then there is no change in the garnet composition, and there should not be any change in the melt composition. So you generally you're going to verify immediately if the garnet is homogeneous or not. And once you verify that it is homogeneous, you can reasonably assume that also the melt inside will be homogeneous in that volume, right? So once, basically what I'm trying to say is that bigger or smaller, once you break them, they get small enough. And they are all the same size because you have to fit them inside this tiny chips. So the approach is exactly the same when it comes to the experiment. In some cases, if you have garnets that are zoned, for instance, and you need to really go and get a special area, you can use micro drilling, which gives some very nice results. But so far, in all my case studies, I was just working on double polished fixed sections and just cracking them, selecting them. Basically, what I do, I look at them under the microscope and I break them with a razor blade, and I select like this my experimental material. So when you are on the field, of course, as you said, in the Bohemian Massif, they are significantly smaller, so they can be contained into a slice in a thin section or fixed section. When you go to the Adirondacks, well, the sampling technique was actually pretty cool, because unless you have some big tool that can actually cut a 30 centimeter wide garnet out of the matrix as a whole, the only thing you can do is hammer it right in the center, and these garnets are extremely cracked without alteration, but they just have a lot of cracks. And you just hammer it in the middle, and it becomes like a bump of tiny bits.
Yeah, they break apart into 100 pieces. Yeah.
You just scoop it with your hand. And when you go to look, because then we did the check, we went to check if the composition of the garnet was always the same across all these pieces. It is exactly the same. I mean, there is a slight variation in magnesium when you go toward the rim, but then it is influent to us because there are no inclusions at the rim. They are always in the inner part. So, yeah.
Oh, that's nice. And also, I was interested because you really focus on the garnet because it's a perithetic phase. So the melt inclusions will be derived from, the prograde part of the PT path during the prograde stage. And then in this recent collaboration with Maira, that now you are analyzing the melt inclusions in zircon. And most of the zircon, usually they grow in the heterograde part of the path. So during the crystallization of the melt. So how do you actually, you're going to bracket the melt composition? I mean, compare the melt composition from perithetic prograde phase and then compared with the zircon? I mean, or you should expect a similar composition of the melt, or what are you planning to?
Well, of course, this is a major challenge, trying to understand where the zircon form. But even if, I'm not an expert, I'm kind of becoming more of an expert as time goes by nowadays. But as far as I know, one can bracket, for instance, by comparing the distribution of the trace elements between garnet and zircon, you can see if there is some contemporary growth of these two phases or not. If we find inclusions in both, then we can, do some kind of correlation. Of course, as you say, in most cases, we will find probably nanogranitoids that are melt, it's a little bit evolved, of course, because it's something that it's already during the cooling path of these rocks. But this is the problem. Each case will be slightly different. Then there is the major problem of distinguishing, are we looking at nanogranitoids or crystallized melt inclusions in that case, or nanorocks or whatever, that are from the original history of the protolith, or they are actually metamorphic? Because yes, if you can measure them directly, you can verify the age. And in fact, this is one of the nice things of working with zircon. You can measure the age directly. The problem is that sometimes the metamorphic rim is so tiny that you don't know if you have the space to measure it. You don't know even if you have the space to trap the inclusions, because you need to grow a certain amount of mineral to trap some inclusions, right?
Exactly, yes.
So what I'm saying is that, we have been collecting some cool data with my era. In fact, we need to talk about those data at some point. I just didn't have time so far. And, but it's challenging. It's challenging, but again, when I was preparing my latest project, in which I inserted a strong part exactly on nanogranitoids in zircons, I realized that nobody has been doing pretty much anything on this kind of inclusions. More recently, this year, a paper came out which rehomogenized crystallized melt inclusions, but in magmatic zircons. It's from the group of someone here in Germany, I don't remember. Anyway, that was the very first paper that was actually going to look at, crystallized melt inclusions in the zircon and rehomogenizing them with a piston cylinder. So, and these were clearly magmatic zircons, so there was no doubt, because they were working on magmatic rocks. But again, it's something new. Someone has to look into it, and we hope to be the ones.
Yes, that's very exciting. Thank you, Silvio.
You're welcome.
Yeah, I think it's also a challenge, Brenda, but when we started thinking about that, Silvia and I thought maybe we can also have like some different composition recording, like peak to retrograde and changing the composition recording this stage. So we are still checking the results, and as Silvia said, there's a lot of challenge on the way, but it's quite interesting, and it's I'm also curious. So Silvio Gautier also said that he...
Go ahead, sorry.
Sorry?
Go ahead.
No, go ahead.
And you're probably gonna be looking for two different populations of zircons. I mean, the really old ones, the 2.5, 2.6 ones, and the 600 million years ones. Yes. That's nice. So looking forward to seeing some results.
Yeah, put the pressure on me, Silvio, now.
No worries.
Gautier. So Gautier has, how do you say, provocated us. I see. He said that rocks from the Araçuaí origin has some nanorocks, and we definitely should look at them. You're right, Gautier. Let's have a talk about that. And Silvio, I have a question myself. I think I have seen with your work and Alessia's work, and that sometimes you have and it is work as well, that sometimes you rehomogenize the inclusion, but you have some left phase. I'm not sure if they are left. Sometimes they can also be results of this interaction with the host rocks. So how should we behave with this kind of inclusion? What is the careful that we should take when we are having this type of results? Because I have seen, depending on the composition, this can be quite common, right?
Well, that's the problem when you're doing dirty experiments, as Bernd Wunder always tells me. By putting these nanogranitoid-bearing garnets inside a capsule and make them go to high PT, and then you don't know what's happening, and then you just have to trust the experimental products and try to interpret them. Yes, it is often that we find nanogranitoids that if they are small and we got the conditions right, they are generally fully rehomogenized even after a very short time at high temperature, even after 4 hours. They are fully rehomogenized. Sometimes, yes, you have, after the experiments, you have glasses and you have other phases. Those other phases, of course, needs to be defined. And the point is, if the same phases are present with the same size in the host garnet as common mineral inclusions, then we interpret them as trapped minerals. So minerals that were trapped during the process of formation of the melt inclusion. For instance, this is common when you see a rutile, like I had a picture of a glass inclusion with a rutile sticking out like that, there was the inclusion like this, and there was this rutile sticking out. And clearly the rutile was already embedded in the garnet when this tiny drop of glass remained attached to that and the garnet grew around it. So in that case there, you have the observation that the mineral inclusion is also present in the rest of the host. And plus, you have a mineral inclusion that is half inside the inclusion, half inside the host. So clearly it was something that was embedded in the host before the closing of the droplet itself. So you can call that accessory. Then it becomes trickier when you have something like quartz, because when you have a nanogranitoid, quartz is often present, quartz or cristobalite, as we have seen. And sometimes after the experiment, you have a little bit of quartz in your inclusion, or even cristobalite. We even found cristobalite after the experiment. And then you can, it's difficult to say if that quartz was an accessory mineral, so a trapped phase, sorry, not accessory, a trapped phase. So it was already there, was present with the garnet, with the melt, and then got entrapped, just like a rutile, just like a zircon. Or it's just that your nanogranitoid is not completely melted. Sometimes it happened that some experiments were not long enough to melt everything inside the nanogranitoid, so you form a bit of glass, but the rest is not melted. So there you have to be very careful, and one way to solve it is that if you can analyze the melt, and you can compare, the glass, if you can compare that glass after the experiment to another inclusion from the same sample where there is only glass, if they have the same composition, then that quartz is not part of the bulk composition of your crystallized melt. It was just a trapped phase. I don't know if I am clear on that. It's a mix of chemical considerations and purely microstructural observation. It's really not easy. When you have some large nanogranitoids, the largest nanogranitoids I've seen are the one from Rico's master thesis. You probably remember him from Pfaffenberg. It's another situation of eclogites in peridotites. Those nanogranitoids are like 50 microns across. For me, 50 microns is a whole universe. It's amazingly big. And those guys, it's difficult to rehomogenize them because you need to leave them at high pressure and temperature for generally longer than, apparently longer than many other inclusions. So.
Yeah, that's nice. So we have some comments. There is a question from Otavio first.
Yeah, there is a question from Otavio. Yeah.
There is also one from Luvisotto, I guess.
Yeah, next one. So Otavio is asking, do you think it would be appropriate to use melt inclusions composition instead of those from segregated leucosome to reintegrate the melting into the residue in order to model a possible protolith?
My answer is absolutely yes. This is exactly why we are doing this. Second, I mean, it's clear that leucosomes are only in rare cases representative of the melt, very rare cases. But I have to say, I mean, I'm not an expert in this topic. I have to suggest you to read Bartoli et al. 2017, and maybe, no, it's not it's just Bartoli. Bartoli 2017 and 18, I think on Geoscience Frontier, and he discusses exactly that point, using the composition of the melt inclusions to reintegrate the melt and then reconstruct the original bulk rock composition. You will find a lot of information there. But yes, absolutely, don't use the leucosome because you will have to do assumptions. You will have to modify the leucosome. If nothing else, the water in the leucosome will never be representative of what was exactly in the melt, but also other components. So yeah, absolutely. Go to read Bartoli. That's a very good paper to understand this problem. Okay. This is.
And then we have the comments from
Georgia.
Yeah.
Mm-hmm.
Okay, so
he's saying that's one more reason to look for inclusions in rutile, because differently from zircon, rutile doesn't survive multiple metamorphic cycles. And so, yeah, he's saying that rutile commonly grows from biotite breakdown during the hydration melting. So that's exactly the same reaction from where garnet may crystallize. So it's like, let's, start looking at some melt inclusions in rutile. They might have the potential to extract like a lot of information.
It could be, no, definitely something that I will try to do now. Thank you for suggesting it. I can see already a couple of problems. The rutiles are dark, so it is difficult to actually see inclusions in them. There are some beautiful samples on which Bernardo worked, where he identified melt inclusions in spinel, like dark green spinels. They are visible. You need to use a lot of light, but if you start looking for them, of course, you do it, and I'm sure that we can find something. What becomes tricky then is that I don't like to use field emission SEM as the first line of attack when I look for nanogranitoids. I like to use Raman. Because the Raman, if you use an electron beam based technique, you can only check the surface. If you use Raman, you can check the surface and underneath, and you can get compositional or non-compositional structural data from the phases. The problem with the rutile is that rutile has, if I'm not wrong, two strong peaks, one around 400 and something, and the other one at 670 centimeters minus one. And it gives incredibly large shoulders in the signal. The problem is that exactly in that area is where you have all the signal of the main polymorphs and phases that you find in the inclusions. So it will be very difficult to verify that what we see are actually nanogranitoids with the Raman. But you never know. Maybe working on 30 micron thin sections instead of thick sections, as I do normally, will help. Yeah, I have to think about that. But hey, if Georgia has some nice samples that maybe show some dots, please contact me, okay?
So we have a comment from Lucas Tesse. He said it was a great presentation. Water fluxed melting is one of the most common process of magma generation in the crust. And then he comes with the question. Usually when melting takes place in the presence of water, the perithetic phase formed is hydrated, for instance, amphibole. How can we investigate the nanogranitoids formed by this process?
I do not agree entirely with the statement that water flux melting is that common. I am more with Weinberg and Azalova that says that oh no, well, actually they were talking about water. No, okay, what I believe is that is not water, it's COH fluid. Because when you go and look at it, it's not a simple a simple fluid just like water. It's calling it only water is a simplification. So I would say is a COH, especially in the crust when you have so much graphite. I mean, having carbon is just common. Then, to be honest, I have more experience on felsic systems rather than mafic systems. And yes, I am aware that there are several cases of partial melting of mafic systems where you generate peritectic amphibole. And I looked at some of them. I think there is a lot of this in Sardinia, where I'm going to go at the end of the year. I'm looking forward to see some of those rocks. But so far, I didn't get any experience on that. But just by applying my common sense based on other case studies, in amphiboles, you may possibly find some melt inclusions. I mean, you need to have a peritectic phase growing in presence of melt. Fine. If that box is checked, then you have the chance to have nanogranitoids or nanorocks. But in an amphibole, the problem is that the amphibole has a weak structure. It's not tough like garnet. So even if you find the nanogranitoids, I would expect them to have been sort of open, have lost something, maybe some water or something. I'm not sure. So far, I looked into some rocks where the amphibole could have been peritectic. I didn't see absolutely anything. Yeah, I would say let's find nanogranitoids in amphiboles and then let's see what we can find. My guess is that we try to rehomogenize them and we can't rehomogenize them because they have lost fluid. That's my guess. But yeah, maybe I'm wrong. If I'm wrong, it's better because this means we can do more stuff. So.
So thank you, Silvio. There are several people thanking for your presentation.
Thank you.
And I would like once more to thank you for coming, and also thank Kae and Brenda for joining. They are our collaborators, and today they come to be part of as host as well. And to thank everybody from the crew that could not be today, but they are working on the backstage to make PTt-talk work. So that's it. Thank you so much, and see you soon, hopefully.
Yeah, hopefully.
Thank you.
Thank you, Silvio. It was really great.
Thanks. I'm glad you appreciate it. I hope nobody fell asleep.
No.
No.
It was really a pleasure. Thank you again for inviting me. It was my first big talk online with such a big audience, actually. Okay. Thank you very much again.
Thank you, Silvio.
Okay.
Thank you.
Bye-bye.
Bye.
Bye.
Ciao, ciao.